Welcome again to Let's Talk Advanced Chemistry 2 with Pastor Dan. We're going to look at the last concept in bonding. It's a different way of looking at covalent bonding. It's called molecular orbital theory, right over here. Now, molecular orbital theory is defined as the theory to explain the process of covalent bonding. Now, this differs from what we've been looking at so far, and that's referred to as VSEPR, valence shell electron pair repulsion theory. Okay, so the idea of that theory is that we're going to move the electrons as far apart as possible. This one focuses more on the bonding arrangements and the structure that exists inside of that. All right, in order to do that, there are a couple terms we need to identify. We need to identify a sigma bond, a pi bond, an anti-bond, and bond order. Sigma bond is defined as a single bond. So if we have a sigma bond, that's the same as a single bond. A pi bond is what we refer to as a double bond or theoretically even a triple bond. Those would be pi bonds that exist above and below the plane of the bond. Okay? Anti-bonds are unstabilizing bonds so that when a bond begins to form, these will cause it to become less stable. And if we end up with a reaction where a bond where the structures form up to be zero, that means the bond can't take place because it's too unstable. And then last is something called bond order. Now, bond order, to find that, we take the number of bonds minus the number of antibonds. That number divided by 2, and that'll give us like the single bond, a double bond, triple bond, how the structure is formed out. All right, let's take a look at the process. Okay, so what we're going to do here, we need this arrangement. These are referred to as our sigma bonds. This little star here means my anti. So I've got a sigma anti, sigma pi pi, pi pi, pi anti, sigma anti. And we're going to identify the number of valence electrons. So I've got a chlorine to chlorine bond. So first thing I'm going to do is identify the number of valence electrons. Okay, so from the periodic chart, which is right over here, we see that chlorine has 7 electrons. And since they're both the same, they're both 7. So that means you have 14 electrons to work with. Now we're going to put them in the same as we did for electron configurations for quantum numbers. We're going to talk about that again here coming up real soon. That's from Chem 1. If you need to go back and look, we're going to look at it again here coming up next. So we have the first bond in, that's 1. The second one in, that's 2. Then third, fourth, fifth, 6. Now I've got 8 more to go. I'm going to put them in 7, 8. I put 1 in each of the pi bonds. 9, 10. Now I'm not going to keep doing this, but I've got 4 more to go. They go there. So that's all the structures we do. Now to find the bond order, we have 1, 2, 3, 4, 5, 6, 7, 8 pi's. And I have 1, 2, 3, 4, 5, 6 antis. I mean, 6 bonds, 8 bonds, 6 antibonds. So we put those in. 8 divided by minus 6 is 2, divided by 2, that's going to give us 1. Now, does this agree with the VSEPR? Yeah, it does, because I got a single bond here, bond order is 1. It's in agreement. All right, let's try another one. This time, let's do nitrogen. Nitrogen is over here. So we have 1, 2, 3, 4, 5. So we have 5 on each one. So that's 10. 10 electrons. Put them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. Now, bond order. 1, 2, 3, 4, 5, 6, 7, 8 again. And antibond 1, 2. 6 minus 2 is 6. Divided by 2 is 3. So bond order is 3. Does that agree with VSEPR? All right, let's see. That's a triple bond, so that does agreement. How about paradiia? What do we mean by paradiia? Well, it has to do with the magnetic nature of the bond. The definition is paramagnetic means a bond with magnetic character. Dimagnetic means no magnetic character. How do we identify that? Well, if you look at the structures, and if they're either equal or they're like 2 or 1 or both filled up, that is dimagnetic. We don't have an open spot. If we're in pi and 1 is open in each one, that gives an electron for one one part to go, and then another molecule to come in the other side. So that gives us magnetic nature. So it's paramagnetic if pi has one on each and there's open spots, or sigma one on open spots. If they're not, then it's diamagnetic. So let's go through and see what this would be. In this case, we see that my pi's are totally filled, so that would be diamagnetic. Let's see one that would be an example of a paramagnetic. So let's look at oxygen. Take and do this one on your own, and then we'll go through and discuss it, okay? All right? Pause it, work through it. Remember to like, share, subscribe. Any questions, ltswpd@gmail.com. All right, here we go. Okay, so take your time, put the values in, identify the bond order, identify if it agrees with VSPER, and then identify it as paramagnetic or diamagnetic. So bond order is 2. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 4 divided by 2 is 2, so that, and it does agree because we end up with a double bond. It's paramagnetic because in pi I have one open spot here. If it was down in sigma, anything else is diamagnetic. All right, that is our answers. Hopefully not too bad. Take care. God bless. Bye.